So our next talk then would be investigating the cause of variability in epi-low-bow quasar SDSS phone number. So, and this is by Sophia Pasquini from the University of Western Ontario. So anytime you're ready.
Okay, thank you. All right, so hello everyone. My name is Sophia Pasquini, and I've been working with Dr. Gallagher and PhD candidate Kaylee Green here at the University of Western Ontario in Canada, in conjunction with the research group at the University of Oklahoma, led by Dr. Laley, including Joseph Choi, from whom we've just heard, as well as Dr. Donald Turndrum from Ohio State University, and of course, many more who are not listed here. So I'll be talking to you all today about our work towards determining the cause of variability in iron low-bow quasar J1229 plus 2621. So on the right here, I've got an artist's rendition of the winds that are launched from quasars. And these winds or outflows are extremely powerful and are believed to be one of the mechanisms by which quasars interact with and affect their host galaxies. As you may know, quasars are extremely difficult to study, and so in the context of relevant literature, the structures and kinematics of these outflows are severely understudied and generally poorly understood. For this project, I have fit a total of 3 spectroscopic observations for a quasar which has been confirmed to be varying in the time domain, and I've done this in order to constrain physical parameters which model the outflowing gases in this quasar. I do this all in the hopes of coming to better understand the mysterious and exciting relationship between the evolution of the host galaxy and the central black hole. So just as a formality and a refresher from the intro we had from Joseph, we define a broad absorption line quasar as one which has characteristic broad absorption lines which have been significantly blue shifted from their emission lines. And this category of quasars is split further into present spectral features, or according to present spectral features. So a bow quasar, a broad absorption line quasar, which has been observed to have both high and low ionization energy species present, in addition to excited state iron 2 or iron 3, is classified as an iron low ionization bow quasar, or an iron low bow quasar for short. So this category of bow quasars is the most rare out of all bow quasars, and it only makes up about 0.3% of the, or sorry, 0.3 of the quasar population, so about 30%. So iron low-bow quasars, however, have the highest gas column densities, and when coupled with the high velocities of their gas outflows, these objects have the ability to produce the most powerful bow quasar outflows. So since the regions of interest for studying quasar outflows cannot currently be spatially resolved, we rely on spectral variability studies to guide our understanding of the origins of these outflows. So here I've included 2 optical and UV spectra for the iron low-bow quasar that I'm studying, and they were taken from the SLOAN Digital Sky Survey. The first epoch was taken in April of 2006, and it's given in red, and it was taken using the SDSS spectrograph. The second epoch was taken nearly 7 years later in 2013, and it's given here in orange, and it was taken using the BOSS spectrograph. So we can see that this quasar is definitely exhibiting variability. For example, we notice there's a higher flux in the second epoch, and we even notice changes in the structures of some of the absorption features. So by studying these changes, we can begin to think about what kind of physical implications these changes imply in the context of the outflow that we're probing. So in purple here, I've just highlighted some prominent, broad, and deep absorption lines. Radiation pressure from continuum emission in the quasar drives these winds and results in these characteristic broad absorption line signatures. These winds impact aspects of the host galaxy, as I've mentioned, such as star formation and the size of the bulge, for example, due to removal of materials for star formation and the improvement of accretion efficiency, respectively. So we do not fully understand the physical qualities of the region from which these outflows originate, or the mechanisms by which they vary. So by studying the broad absorption lines in Bal quasars, we are directly probing the outflows in hopes of learning more. In the case of the broad absorption lines in iron low Bal quasars, we're probing the most rare and powerful quasars because they act as vital tests on existing or proposed quasar outflow models. So just minutes ago, Joseph Choi gave us an excellent introduction to SymBal, the spectral analysis software, which was developed by him, Dr. Laley, and the rest of their group. And I've had the privilege to collaborate with them and use this software in order to carry out my variability study. As a refresher, I've put together this diagram to hopefully help illustrate the general idea of how SymBal works. So we start by supplying the observed spectrum and our initial best guess at what we think the model is going to look like to SymBal. And from there, the software is able to use pre-calculated photoionization codes in order to construct a synthetic spectrum, which it tunes to the original using a Markov chain Monte Carlo algorithm. The algorithm then outputs a final best fitting model based on the information that we gave SymBal. From this best fitting model, we're able to directly extract numerical values of the best fitting parameters from the spectrum that we wish to fit. And these are what form the foundation of the large scale outflow models that we wish to build. So over the last year or so, I was able to successfully use SymBal in order to model both spectra for two distinct epochs for the variable quasar that I'm studying. Here I've included both of these, the current best fitting models. The actual spectra are plotted in gray. The continuum components from the models are given in yellow, and the total output SymBal model is given in red. We note that there is a larger wavelength coverage in the spectrum on the second epoch than the first, because as I mentioned earlier, there is a discrepancy in the instrumentation used between the two epochs. So we can see that these models do a pretty good job at capturing the shapes of the continuum and the absorption features in each case. So using the best fitting models for each epoch, I was able to directly extract the associated best fitting parameter values for each of the model parameters. So some of which I've plotted here to illustrate how the physical state of the outflowing gas is changing in time and velocity. So the x-axis of each panel here is the velocity offset given in units of kilometers per second. And I'm able to plot these parameters in this way because the model spectra for both epochs use a top hat accordion function to model the absorption features. So each absorption trough is separated into 5 independent velocity bins from which we can extract information. So that's why you see 5 distinct points per parameter per epoch on this plot. I've illustrated changes in time by coloring the points of the parameters distinctly. So to make things a little more clear, I've also calculated an average % change in time for each parameter. So we see in the top 2 panels that the ionization state and the density of the gas decrease from the first to second epochs, though they remain constant as functions of velocity. When converted from the logarithmic scale, their % changes in time are roughly 45% and 95% respectively. Taking a look at the column density in the third panel, right away we see that it doesn't look like it's changing as significantly in time as the ionization parameter or density, or changing in velocity at all. The average % change is about 13%. But that being said, when we take a closer look, we see that SymBal actually formulates the column density with respect to the ionization parameter. So this is changing in time. This means that in actuality, the column density parameter alone must also be decreasing in time. So here we have the spectrum that we obtained from the Apache Point Observatory in blue, overplotted against the data from one of the optical spectra for this object in gray, and its corresponding SymBal model extended to a longer wavelength regime in red. We originally wanted the APO spectrum so that we could calibrate the redshift for this object, as well as calculate the black hole mass. After obtaining the infrared spectrum from APO, we immediately notice that there is absorption in the H alpha line, as well as maybe a hint at what might be absorption in the H beta line. We thought it might be an interesting experiment to extend the symbol model that we had for this epoch into this object into this wavelength regime. And we were happy to see that it was indeed able to predict this rare absorption. So this absorption has only been observed in a handful of Bal quasars to date. So it's something that's very exciting to be able to observe, and even more exciting is the fact that the models from SymBal were actually able to correctly predict this absorption, given the fact that it's so rare. So not only were we able to meet the science goals that we originally intended for this spectrum, but we got the bonus of seeing the Balmer absorption. So using Sherpa, I was able to model the emission of both the H alpha and H beta lines, which we can clearly see here on the spectrum. Using the model position of the H alpha feature, as well as other lines, we were able to calibrate the redshift of this quasar to be about 2.6. We are also able to directly extract from the spectrum the physical radius of the broadline region for this outflow, which we estimate to be approximately 855 light days from the central supermassive black hole, which we also estimate to have a mass of about 1.13 times 10 to the 10 solar masses. We are able to directly calculate the bolometric luminosity from this quasar. For this quasar, we estimate about 4.5 times 10 to the 47 ergs per second. And not only were we able to confirm the Balmer absorption as predicted by the extension of the SymBal models for the UV and optical spectra, but we're able to use this spectrum to derive luminosities and other vital physical quantities for this quasar using well-calibrated lines, which we did not have access to without APO. So I cannot emphasize enough how valuable of a resource this spectrum has been to the project. So using the extracted best fitting parameter values from the SymBal models, namely the ionization parameter and density, we were able to derive a preliminary radial location of the outflow with respect to the central supermassive black hole. Future work on this project includes the derivation of the mass loss rate and kinetic luminosity, which is ultimately what we would be after, as it is a gauge on the impact the quasar's outflow has on the host galaxy, the relationship that we're probing. And further, a joint fitting will be performed using a newly discovered SymBal functionality in order to test and verify the best fitting models. These results yielded will be used in order to complete the large-scale dynamical model for the cause of variability in this windy quasar. This brings me to the end of my presentation. Thank you so much for your attention.
Thanks. That was a great talk. Appreciate it. Any questions? Any hands raising? So your prediction of Balmer absorption and the actual observation of it, I thought was just really cool.
Right.
I guess my question there is, do the Balmer lines have the same sort of velocity coverage that the other lines that you'd already looked at have? In other words, you know, they span the same velocity range?
I imagine that they would. Do you mean as far as the SymBal model? Like
yeah,
what we
as
got
far
from
as
the
just,
SymBal
yeah,
model?
or just a direct comparison with the other absorption lines. You know, they looked fairly narrow in the spectrum that you showed, but I didn't quite get what the width of the other lines were.
Right. So we didn't actually model. I can go back to that slide actually.
Sure.
So we did not actually model the spectrum in this wavelength regime. We just took I think the maximum wavelength that we modeled the original spectrum in was like 2,900 angstroms or something like that. And so we just extended it just to see what it would look like and see if it would be able to predict that absorption, and it did. It looks a little bit narrow, I think, on here because I guess the wavelength scale is off, but I would imagine they would have the same velocity scale as the other lines.
All right. Well, again, it's a really cool result. So congrats.
Thank you.
If there are any other questions, please feel free to post them on the Slack channel. Okay.